So still looking at section 6.2. This is our second day of volumes of solids with known cross-sections. And today we're going to focus on cross-sections where we have information about them being taken perpendicular to the y-axis. Last time we looked at cross-sections that were perpendicular to the x-axis. I only have one example I'm going to show you today. We're going to do two different parts of this example. A solid has a base given by the region bounded by y equals the cube root of x and y equals x squared. We're going to find the volume of the solid with cross-sections of, we're going to look at two different shapes in a moment, and we want these cross-sections this time to be perpendicular to the y-axis. And we'll start the way we pretty much always do with these problems, and we're going to say that our cross-sections are squares. Well, first thing we need to do, as always, is sketch the region we're dealing with. I think you should have a good idea of what y equals the cube root of x looks like and y equals square root of x. But if you just go to the calculator at this point, that's fine. Y equals cube root of x is like that. Y equals x squared is like that. They intersect at 1, 1 and 0, 0. And my cross-sections are looking like this. Those are bases, in this case, of squares sticking out of the page towards us. Before we go on and talk about the calculations, let me show you what this solid looks like I did last time with those videos. So there's my square with a cross-section perpendicular to the y-axis this time. Here are several of those squares. And here's the entire solid that we're creating. Sort of like that. So our bases of the squares are those horizontal strips over there. And here's one of the squares. Because our strips are horizontal, I can't do a top minus bottom thing to figure out the length of it. I need to figure out the right minus the left. Also, though, remember from our solids of revolution, anytime we dealt with horizontal representative rectangles, which in this case are the equivalent of those horizontal bases, we can't use functions of x, but instead need functions of y over here. Rather than calling this function y equals the cube root of x, I'm going to call it x equals y cubed. And rather than calling this y equals x squared, I'm going to call it x equals square root of y. I don't have to bother with the negative square root because that's the part over here that's not going to matter so much. If you do the right function minus the left function, you're going to do the square root of y minus y cubed. It's a square, so the height of the square is the same thing, square root of y minus y cubed. To find the area of that square, we'll do square root of y minus y cubed, and I'm going to square that thing. And then to find the volume, I'm going to integrate. And because I'm dealing with y values here, horizontal strips, y values, functions of y, I need to integrate over my y values. My lowest y value is 0. My highest y value is 1. So I'm going to go from 0 to 1. And I'm going to do square root of y minus y cubed squared dy. At this point, go to your calculator, do fn int. Remember, it doesn't matter if you type it in using an x or using a y. It's just the name of the variable. It doesn't affect anything on the calculator. And I'm pretty sure that you're just going to get a decimal for this one, and that's going to be fine. So I'm getting about 0.198 for that volume. One more example here. Letter B, let's say that instead our cross-sections are right triangles with a base in the xy plane xy plane, still perpendicular to the y-axis. and a height 3 times the base. This time I'm dealing with right triangles with a base in the xy plane, so those horizontal strips that you're seeing are the bases of those right triangles, and a height 3 times the base. I'm going to go draw in one of those triangles. One of those strips matches up with the base over here. I needed to do that right minus the left, still sticking with those functions of y. It's the same base I had in the last problem. I'm going to say the square root of y minus y cubed. And as for the height, it needs to be 3 times that thing. So I'm going to say 3 times in parentheses square root of y minus y cubed. The area of that triangle is 1/2 base square root of y minus y cubed times height, so times 3 times the square root of y minus y cubed. We can condense this thing and turn it into a equals 3/2 times square root of y minus y cubed squared. To find the volume, I'm going to integrate over the y values for my region, so I'm going to go from 0 to 1 of 3/2 times the square root of y minus y cubed squared dy. You could go to the calculator, or you could factor out the 3/2, make it 3/2 times the integral from 0 to 1 of the square root of y minus y cubed squared dy, and then just do 3/2 of the answer that you got from part A. And if you do that, you're going to get a volume of about 0.298 over here. And that's it. Actually, let me show you what this one looks like, so hold on a second. Well, apparently I can't show you that. The program doesn't let me do triangles with any particular heights, just those isosceles triangles from last time. But hopefully you kind of have a sense of how this stuff works. If those cross-sections are perpendicular to the x-axis, you need functions of x, and you're going to integrate over your x values. And if they're horizontal cross-sections, if they're perpendicular to the y-axis, you need functions of y, and you need to integrate over the y values. That is it for today, and actually that is it. This is the last topic in AP Calculus. We are done. We'll practice a little bit of this, and then start getting into our review for the AP exam. We made it. See you later.